All right, let's get started. So hopefully all of you guys have gotten a chance to start on homework 3. If you haven't, please do make sure to start on homework 3 because the training times are going to be a little bit longer and you want to make sure that you have enough time to finish everything. But today we're going to talk about model-based RL and policy learning. So last time we talked about how we can learn models of dynamics and then use, so that we can then use optimal control to choose actions. And we very briefly discussed how we could also use learn models to learn policies directly so that we don't even have to do any planning at test time. And today we're going to get a lot more into this topic of how we can learn policies from models. So last time we talked about global models and model-based reinforcement learning. We also talked about local models and how you can use local models with model-based reinforcement learning and how it really helps to introduce some constraints so that your modifications actually remain local, so that your local model actually works. But today we're going to talk about what happens if we actually want a policy instead of just a model. Getting a policy has a few advantages. It's much quicker to evaluate actions at runtime, but also, and perhaps more importantly, it can actually produce better generalization. And the rationale for this is that sometimes you might be able to get good models in the region where you visited, use that to acquire a policy, and the policy can actually generalize more widely than the original model. And I'll give an example of that later. So one of the things we talked about last time is, well, can we just like back propagate into the policy? Can we build a computation graph that has our model in that computation graph, push gradients through that graph, and actually compute the derivative of the reward with respect to the policy parameters? And we talked about how there are a few disadvantages to that. We'll cover those in more detail today, and then we'll talk about how to address those disadvantages. So in today's lecture, we're going to talk about back propagating into a policy with learned models and how to make that actually work fairly reliably. We're going to talk about how this actually becomes equivalent to imitating optimal control, so we're going to actually tie things back to the imitation lecture from earlier in the course. We'll talk about the guided policy search algorithm and also about imitating optimal control with Dagger. So we'll talk about two ways that imitation learning and model-based RL actually come together. We'll talk about, at the end, about trade-offs between model-based and model-free methods. Now that we've covered both model-based and model-free algorithms, we'll discuss when either of the two might be appropriate and how you can decide which one to use. So the goals of today's lecture will be to understand how to train policies using optimal control, understand the trade-offs between the various methods. So how can we train policies? So far we saw that we can train global models like Gaussian processes or neural networks. We can train local models, for example, using the linear regression technique that I covered on Monday. And I very briefly mentioned how we can combine global and local models, for example, by using Bayesian linear regression. And this was very brief, so if you don't remember it, don't worry about it. But what if we want a policy? Again, the advantage is that maybe you don't need to replan, so it's faster, and the better generalization. So let me talk about the better generalization a little bit. And let me first illustrate it with an example. So imagine that you're playing a sport like baseball, and you'd like to catch a ball. A model-based RL approach to doing this would be to say, well, I'm going to model the physics of the environment. I'm going to try to understand how objects fly through the air, how they're affected by gravity, how they're affected by wind, solve a planning problem and figure out the predicted landing location of the ball, and then I'm going to run over there and catch it. It actually turns out that the way that people and animals solve this kind of problem is a lot simpler than that. So there's this very widely known phenomenon called the gaze heuristic. And the gaze heuristic works as following. If you're trying to intercept a flying object, what you can do is you can look at that object. If it's a ball, it's just like a dark spot against a bright sky. And you memorize where it is in your visual field. And then you start running, and you modulate your running speed so that point stays in the same spot in your visual field. So if it dips down a little bit, then you speed up. And if it rises a little bit, then you slow down. And if you follow this very simple heuristic, so you're not actually planning for anything, you're just reacting to the ball, you'll actually arrive at exactly the spot where it lands. So this is an instance of a situation where the policy, the relationship between observations and actions, is actually a lot simpler than the underlying physics that govern this interaction. So the point of this example is to illustrate that there are situations where acquiring the right relationship between observations and actions will actually produce superior generalization to figuring out the underlying model of the environment. So even if you can acquire a model in, let's say, a few situations, maybe in a few training settings, it might actually be desirable to then distill that knowledge down into a policy and then use that policy to generalize to new situations. So if you were to, for example, acquire the gaze heuristic, it doesn't even matter how you acquire it, whether it's with a model-based or model-free method. If you acquire it from practicing, catching a ball, you can also use the same exact rule to intercept any other flying object. Actually, if you learn to fly an airplane, for example, one of the things that they might teach you is that if you want to figure out if you're going to collide with another airplane, just look for a little speck of dust on your windshield and see if that other airplane moves relative to that speck of dust. If it doesn't move, that means that you're going to hit. All right, so point of the story is that sometimes, even if we can acquire a model, turning that into a policy can result in better generalization. Okay, so one of the things that we discussed on Monday is that if you want to learn a policy, you can construct a computation graph, and that graph consists of basically the three objects in your RL problem. And here I'm going to use costs, x's, and u's, but if you want, you can mentally substitute r's, s's, and a's. It's all the same. So the three objects in your RL model, in your RL problem, are going to be the cost or reward, the model, the system dynamics, and the policy. So model or system dynamics, cost, and policy. And if you have all of these three things, if you basically have differentiable representations of all three of these things, then you can do backpropagation and compute the derivative of the total cost with respect to the policy parameters theta. So one might think that if you can compute these derivatives, then that means that you're basically done. But unfortunately, it's not quite so simple. So you can compute the derivatives, and that's absolutely true. And it's actually fairly easy for deterministic policies, and it's even possible for stochastic policies and stochastic dynamics, for example, by using the moment matching trick that I discussed when I talked about Pilko on Monday. But there is and the resulting algorithm would look something like this. This is the version 2.0 that I talked about on Monday. You run your base policy to collect some data, use that data to fit your dynamics, backpropagate through the dynamics into the policy to optimize the policy, run the policy to collect more data in order to address the distribution mismatch problem, and repeat. So this is the backprop into the policy algorithm. So there's a dark side to this, and the dark side is the following. Over here, the action that you choose at the very beginning has a big effect on your cost because it's going to change all of your future states. So the gradients right here are going to be very big. At the very end of this graph, the very last action you choose has minimal effect on your total cost because it only affects the last time step, and even then probably not very much. So the gradients at the end, I mean, obviously this is only 2 steps, but imagine this is like 1,000 steps. The gradients at the end are going to be small. So huge gradients here, small gradients here. You can imagine this visually, that if your trajectory is this little curvy line, if I'm changing the action over here, this whole thing is going to swing around pretty wildly. So even a small change to an action early on is going to wildly change the behavior later on. Imagine you're holding like a really long stick, a little tiny motion of your wrist will change the tip of that stick by a very large distance. So this ends up with kind of the world's worst ill conditioning problem. This is a similar parameter sensitivity problem as shooting methods. So when we talked about shooting methods for trajectory optimization before, one of the things I mentioned is that, well, you could do gradient descent for optimizing trajectories. In practice, that doesn't work very well, and that's why we went through all that trouble of figuring out LQR, iterative LQR, which is basically a second-order method. It's basically Newton's method for trajectories. So for policy optimization, there is no longer a convenient second-order LQR-like method because the policy parameters couple all the steps, so you can't do dynamic programming because the same parameters couple all the steps together. And the challenge with these big and small gradients is very similar to the problem of training long recurrent neural networks with backprop through time. So if you're more familiar with recurrent neural networks, one of the things that you might have heard about is the problem of exploding and vanishing gradients in recurrent neural networks. And this is essentially the same problem, but much, much worse. So with recurrent neural networks, oftentimes what people do is they actually choose recurrent neural network representations like LSTMs that are nicer, that have nicer gradients. The trouble is that if we're modeling dynamical systems, we don't get to choose what this thing is. We have to learn the physics of the world, and the physics of the world might not be nice and well behaved. They might not have nice gradients, and if we fit them accurately, our model will also not have nice gradients. So the challenge with backprop into the policy is very similar to the challenge with training RNNs with backprop through time, except that now we don't get to use all the tricks that we have for RNNs, like LSTMs, to make them more well behaved. Okay. So what about these collocation methods? Those of you that were that remember the lecture last week when I talked about optimal control might remember that I said that there's shooting methods and then there's collocation methods. And collocation methods in optimal control are algorithms that optimize a cost or a reward, and they use a constrained formulation. So instead of taking this equality constraint and actually folding it inside the objective to produce an unconstrained optimization problem, they actually keep the problem as a constrained optimization problem and optimize either over states or over states and actions. So graphically, we could imagine this like this, that we're actually going to keep track of what all these states are. Even though the states are just a consequence of your actions, we'll keep them as variables anyway, and then we'll actually move them around in order to improve our trajectory. And now, if you keep track of the states explicitly in your problem, now you don't get this problem of enormous sensitivity because you get to move around the individual states rather than just relying on changing the actions. The downside is that now you have this constraint to take care of, so you need some way to actually enforce that constraint. Okay, so that's for optimizing trajectories, but we're interested in optimizing policies. So can we use the same trick for optimizing policies? Can we say, well, if you have a policy pi, let's actually introduce that policy not as a node in our computation graph, but as another constraint. So we're going to say, well, we'd like our actions to not just be arbitrary, but we'd like them to be produced by pi. So we'd like the action to be a function of x, and specifically this function. And then we'll just add this as a constraint. We'll have the cost or reward as our objective, and the policy parameters now enter as parameters into this optimization, along with the states and possibly along with the actions also. You can actually, if you'd like, you can remove the actions from this optimization as variables and add another constraint that says u is equal to the inverse dynamics of x and x prime. We won't cover the inverse dynamics formulation here, but that's a very popular way to reduce the number of variables in this optimization. So to summarize what we just did, we said now instead of making a single computation graph with an unconstrained objective that has these very, very sensitive gradients, we'll instead introduce the policy into a constraint and explicitly optimize over the states that we'll visit, subject to the constraint that the actions we take should be a function of the states, and specifically this function. OK, does anybody have any questions about what we just did here? Yes?
I'm confused as to how you can choose the x's if they are constrained by the dynamics.
Well, so that depends on how you solve the constraint optimization problem. So there's many different methods for solving constraint optimization problems. Some of them use linearization, some of them do some sort of relaxation. And this basically allows you to first write down the problem and then pick your favorite constraint optimization method to solve them. So you're right that if you want to enforce feasibility every single step of the way, the problem is exactly equivalent to what we had before, which is kind of the point. It's the same problem. But this lets you sort of get access to a larger range of tools in your arsenal for solving this problem. And in fact, a very convenient way to solve these kinds of collocation problems is to do some sort of relaxation. For example, a very common relaxation is to linearize the constraint and do something like sequential quadratic programming. Yes?
So wouldn't that also involve like putting these collocation points, because that's also like extra degrees of freedom that you can...
Yes, of course. So and that's what this is. So these points, they're all the x's. So you're introducing additional degrees of freedom into your problem. Exactly. OK, now we can abstract away what we just did a little bit. We can say, in general, you have some kind of trajectory optimization problem up here. You don't really care very much how you solve that problem, but you care that you're able to constrain it according to this constraint that says the action should be a function of the state. So this is some kind of trajectory optimization, and actually any trajectory optimization algorithm that accepts constraints can be used up here, so long as you can put this constraint on it. So now we can separate out the two important bits of this, the trajectory optimization up here and the constraint that says the action should come from the policy down here. Yes?
I guess I should have asked this last slide, but what about if so in this case, are we restricted to deterministic policies?
So I'll actually talk about stochastic policies and dynamics later on, but for now, this whole derivation will be for the deterministic case, and I'll actually mention stochastic stuff later. OK, so now, of course, what we need to figure out is how can we impose constraints on a trajectory optimization algorithm? If we can solve a constrained trajectory optimization algorithm specifically with this constraint, then we're done. That's the main thing we need. So how can we impose these constraints? And what we're going to do is we're going to revisit an idea from Monday, which is dual gradient descent. So dual gradient descent is a pretty convenient way to put a constrained optimization problem into into a solver that can solve unconstrained optimization problems. So just to review, in dual gradient descent, if you have some generic constrained optimization like this, minimize f of x subject to c of x is equal to 0, what we saw on Monday is that you can write down the dual function. In the dual function, you can treat the x that minimizes the Lagrangian as a function of lambda of your Lagrange multiplier. So x star is argmin of the Lagrangian at lambda. And then you can write down the derivative of the dual function, which is just the derivative of the Lagrangian with respect to lambda at the point x star. And then you get the following algorithm for solving your constrained optimization. Minimize your Lagrangian with respect to your primal variables, compute the gradient of the dual, and take one gradient step on the dual. And the gradient of the dual is usually very simple because Lagrange multipliers linearly multiply your constraints. So this is usually a very simple gradient. So this is what we saw last time. And last time we saw this when we talked about constraining the trajectory improvement step with local models. Now we're going to use the same trick to constrain trajectory optimization to produce actions that are the same as the actions your policy would have taken. There's a little modification we're going to introduce, which tends to be very helpful for stability, which is that we're going to tweak this dual gradient descent algorithm and make it into what's called an augmented Lagrangian algorithm. Augmented Lagrangian, very simple idea. We have our Lagrangian, and we augment it. And we augment it by adding a funny little term like this. So if your constraint is c of x equals 0, you add a term to the Lagrangian that's some little hyperparameter rho times the square of the constraint. And why would you want to do this? Well, okay, so the resulting algorithm is you just take your augmented Lagrangian, you minimize it, it's exactly the same thing. At convergence, since your constraint is satisfied, this term does nothing. It just goes to 0, so it has no effect at convergence. But far from convergence, it's actually very helpful. So you still converge to the correct solution if you use an augmented Lagrangian. But when far from the solution, this quadratic term tends to really help with stability. So if you're far from the solution, this little linear thing isn't going to be doing very much. But this thing will just tell you, okay, if your constraint is wildly violated, just reduce it. Like, I don't care about Lagrange multipliers, just reduce the constraint. You're too far away. So in practice, this kind of thing, it has all the same kind of guarantees as dual gradient descent. It's not theoretically that different, but in practice, it can be substantially more stable because that quadratic term does a lot of heavy lifting when you're violating your constraint a lot. And then when you get to very low constraint violation, then the regular kind of Lagrange multiplier term is what gets you down to zero violation. And those of you that heard of something called alternating direction method of multipliers, or ADMM, as a side note, this method is basically, this is what you start with in order to get ADMM. So ADMM is just a version of this where you have a particular form of x and f. Okay, so now we can figure out how we can constrain trajectory optimization with dual gradient descent. So our problem, I've rewritten it here in much more concise form. Minimize the cost of some trajectory, subject to the constraint that all the actions along that trajectory should match the actions that your policy would want to take at the states along that trajectory. So this is our sort of collocation version of backpropping into the policy. Our Lagrangian now is going to be given by this. So it's the cost plus the sum over all the time steps of the Lagrange multiplier on that step times pi minus u. So that's just how we write down the Lagrangian. And we want an augmented Lagrangian, so we add this other term that says, okay, let's minimize the squared error. And this is now a very natural term. This is just like L2 error between what your policy does and what your trajectory does. Makes perfect sense. So that's what we're going to use. And our algorithm, just like the dual gradient descent on the previous slide, minimizes Lagrangian with respect to the primal, which you can do using your favorite planning or trajectory optimization algorithm. For example, you can use ILQR if you'd like. And now instead of using it to minimize the original cost, you use it to minimize the augmented Lagrangian, which just gives you a slightly different cost. It's a slightly different cost that now contains the policy inside the cost in the form of this term and this term. Okay, so that's just a trajectory optimization problem. Step 2, optimize the other primal variables, the thetas. And the thetas only participate in these two terms. And the cool thing about these two terms is that they're fully decomposed over time. So now, in the constraint, the policy does not actually couple the different time steps together anymore, which means that you do not need to backprop through time. You just need to solve a good old-fashioned supervised learning problem. Like if you look at what this is, linear term, quadratic term, this is just a funny kind of least squares minimization. So you're just minimizing a modified squared error, right? Because this term is quadratic, this term is linear, so the whole thing is actually quadratic. And then the Lagrange multiplier basically forces you to offset the targets here a little bit based on the size of the Lagrange multiplier. So minimizing this with respect to theta is just a funny kind of supervised learning problem, which you can solve with your favorite supervised learning algorithm, like SGD, for instance. And then step 3, very, very simple. Just increment your, this should be lambda t, increment all of your Lagrange multipliers by some step size times the dual gradient, which is the amount of constraint violation. So fairly simple algorithm that alternates between optimizing trajectories and supervised learning, and then increments the Lagrange multipliers. And this corresponds to optimizing your policy under some dynamics which may be learned without actually having to do backprop through time. OK. Does anybody have any questions about this procedure? Yes?
So, like, typically, how many steps does the
How many steps of this or the whole thing?
the SGD step?
This one. So it's a parameter of the algorithm. So the theory tells you that if you want to use this kind of procedure with dual gradient descent, you need to run this to convergence. Now, there's some other theory that tells you, well, if you don't run it to convergence, it's not that bad. But of course, this is all non-convex and all that other stuff. So in reality, the assumptions of the theory go out the window anyway. So it ends up being kind of a design decision. There was a question back there?
Yeah, I was going to ask if it actually converges, but then you said it was non-convex, and so probably.
Yeah, so all the dual gradient descent stuff, the way I described it, technically requires convexity. There's some like fairly recent work on what happens if you're non-convex, and sometimes it kind of works. But it's very hard to formally extend those guarantees to like basically function approximators where you have no like assumptions like neural nets. So in practice, tends to work reasonably well. In theory, works great if everything is convex, and there's a little bit of a gap in there. Yes.
Can you talk a bit about like what happens in step 3 if you say overshoot 0 on the Lagrange multipliers?
Yeah, so as with any gradient descent algorithm, you have to choose a step size. The nice thing is that the Lagrangian is linear in the Lagrange multiplier. So you see that this comes in here linearly, which means that in particular, this tends to be like a reasonably well-behaved problem, even for a first-order optimization method like gradient descent. And the number of these Lagrange multipliers is small. It's just one scalar value per time step. So yes, you can have horrible things happen here. In practice, it's not too bad. And you can also actually construct a line search. So you can construct a line search against the trajectory optimization step here, and that can kind of work out. So if you're interested in that, I can point you to a paper that does that. OK. So this is the high-level sketch of how we can do policy optimization with dual gradient descent. And what I'll do next is I'll tell you about a few instantiations of algorithms that actually do this. So as a category, we can call these guided policy search algorithms because the trajectory optimization here is sort of guiding the policy optimization by providing targets for it. And if we want to actually construct a practical algorithm, we need to make a few additional design decisions. So the algorithm can be interpreted as constrained trajectory optimization. It can also be interpreted as an imitation learning algorithm because you're sort of constructing an expert here with trajectory optimization, and you're imitating that expert with supervised learning. So that's kind of the connection between model-based RL and imitation learning. So the optimal control sort of acts as a teacher, but it actually adapts to the learner because the objective here for optimizing the trajectory actually depends on the policy. So it'll try to construct trajectories that the policy will have an easier time imitating. So the imitation learning interpretation of it is imitating an adaptive computational teacher, a teacher that is trying to change their supervision based on what it thinks the policy is actually capable of learning. So the general scheme of this procedure is going to basically, this is just a rephrasing of what was on the previous slide. Optimize your trajectory, or in the stochastic case, optimize your trajectory distribution with respect to some surrogate objective C tilde, and that surrogate objective is going to include those Lagrange multiplier or augmented Lagrangian terms. Then optimize the policy parameters with respect to some supervised objective, which typically is going to be the same as the Lagrangian, but the cost goes away because it doesn't depend on theta. And then increment or modify the dual variables. And then what you have to choose if you want to instantiate this algorithm is the form of P of tau or tau. So usually in the deterministic case, everything is easy. Tau is just a sequence of states and actions. But in the stochastic case, you typically need to use some relatively simple distribution class to approximate P of tau. Oftentimes a Gaussian distribution is used for this, and I'll talk about that shortly. You need to choose an optimization method for P of tau or tau. So you need some kind of trajectory optimization-like procedure for step 1. And some of the things that we discussed on Monday or the previous Wednesday can be used here. You need to choose your surrogate cost function. So typically you would use some kind of augmented Lagrangian style objective here, but there are a number of choices. And then you need to choose your supervised learning objective for pi theta, which oftentimes is actually the same as C tilde, but just keeps only the terms that depend on theta. So it looks like some kind of supervised learning objective. So these are the things that you have to choose. And now I'll tell you about 2 examples of algorithms that do this in 2 different ways. So the first algorithm I'll tell you about is actually a deterministic version of this method. And here, this is the augmented Lagrangian, just like before. It's also the surrogate cost C tilde. And what this method is going to do is going to optimize tau with respect to the surrogate objective. It's actually going to do it using a collocation method rather than iterative LQR. But either one could work. It's going to optimize theta with respect to this, just this part of the objective. So that's a squared error minimization. And then it's going to increment the dual variables just by computing the gradient of the Lagrangian with respect to lambda. And this algorithm, it's actually going to do one additional thing, which is that it's going to learn not just with a single trajectory, but actually with multiple trajectories. So let me explain why this is important. Let's say that you'd like to solve some task. Let's make up a toy task. Your agent lives in this 2D environment, and his goal in life is to navigate to the green X. So a single trajectory in this environment might look like this. Start at the red dot and go to the green X. Now chances are, using this one single trajectory is not going to give you a very generalizable policy for navigating to the green X from any location in the world. But if you see many trajectories that all go to the green X, then you have a pretty good chance of acquiring a generalizable policy that successfully does the task from any initial state. So what we can actually do is we can modify this method a little bit so that we're not just optimizing over one trajectory, but over a set of trajectories. We're minimizing the cost of all the trajectories together, and we have a constraint for all the trajectories, but they're all constrained against the same policy. And now we can instantiate the algorithm like this. Where there's a little difference, which is in step 1, you optimize all of the tau i's, and you can actually do it in parallel with respect to their respective objectives. Because if you're just optimizing the tau i's, they're fully decoupled from each other. They're only connected by the policy theta, but the policy theta doesn't change in step 1, so you can actually farm out all these trajectories even to different machines, different servers, whatever, optimize them all in parallel. In step 2, you bring them all together to construct one supervised training set to optimize theta. So theta does couple them together, and that step has to all run together. It's optimizing one objective for one set of parameters. And then step 3, you increment or modify your dual variables, and here it doesn't matter whether you parallelize it because it's so trivially cheap. And then you repeat. So this method, the deterministic variant of this method with a collocation approach for trajectory optimization and parallelization across multiple trajectories, this was described in this paper, Interactive Control of Diverse Complex Characters with Neural Networks by Igor Mardac. And Igor will actually be giving a guest lecture at the end of this course. But for now, I just want to tell you a little bit about this method because it's relatively simple, and I want to show you a video. So the video here is, this is the video that goes with their paper. And what it's going to show is some of the behaviors that are actually learned. So this is showing the final neural network controllers for these little kind of fantasy creatures. And the policy here actually accepts as an additional input a command from the user, which is that green dot. So here, what Igor is showing is he's just dragging that green dot around with a computer mouse, and the creature is reacting in real time using the policy that was learned via this constrained trajectory optimization style approach. So this is just showing the neural network, but the way it was trained was by generating these different trajectories and then using them to supervise the neural net. There are a few interesting properties to these kinds of algorithms. Beyond just allowing you to train a policy, they can actually, in some ways, improve the trajectory optimization process itself. Because if you're forcing your actions to come from some function of the state, that's a very good way, for example, for locomotion behaviors to get a cyclical behavior. So oftentimes, if you experiment with trajectory optimization methods and you try to solve a locomotion task like this, you might get a very erratic gait. Maybe if you were to just do pure trajectory optimization, this little flying creature might flap its wings in very erratic ways, not necessarily in a very nice periodic cycle. But because the constraint forces the action to be a function of the state, a stationary function, it'll actually encourage trajectory optimization to come up with a cyclic solution rather than just an erratic one that gets to the target however it pleases. So there's another example. This is quite a bit more challenging. This is a bipedal locomotion example. Again, the same approach. Many trajectories optimized in parallel across multiple machines and then aggregated together to train a single policy with supervised learning, and then the cycle repeats itself. And again, here, this guy is actually trying to match a user-commanded target. And from all the different trajectories that he saw, he figured out all these different stepping behaviors in different directions, forward, backward, sideways, and so on. Here's another perspective. For a very leisurely walk. Oh, and I should mention that the trajectory optimization procedure, oh yeah, so this is if you have a very strange walking creature. The trajectory optimization procedure here is a collocation method that actually only optimizes over the states and has the actions as a function of pairs of states, so it actually uses an inverse dynamics function. Here's another fun one. So this is a sort of a headless cow-like creature, and it also walks around and tries to reach user-commanded targets. Does anybody have any questions about this?
What was the trajectory optimizer they used here?
So the trajectory optimizer here is a collocation method based on sort of a variant of Newton's method with like what's it called? So it's sort of I'm blanking on the name, but it's a type of Newton's method approximation that uses a block diagonal Hessian. I can look it up if you want afterwards. There was a question back there.
Yeah. So when we say we need quite a few different trajectory, but do we mean that we generate a different initial state or like a different final state, those kind of stuff?
Yeah. Okay. Good question. So what are the different trajectories? So the different trajectories in this case correspond to different initial states and also different positions of the target. So because the guy needs all these creatures are trying to follow a target, the target is actually sampled randomly in the world for each trajectory. There's a question here?
Yeah, actually, what's this platform? Is it open source?
This is actually using a variant of Mujoko. It's just a different renderer. Okay. So now I also wanted to tell you about a stochastic version of this algorithm. And for this one, I'll actually show some results actually with learned models. So the stuff that I showed before uses known dynamics models, so it's not actually learning the dynamics, it's just learning the policy. We can also do this stuff with learned models, so a stochastic variant of this algorithm might use, for example, this local linear feedback controllers as the trajectory representation. Now in the stochastic case, it's no longer individual trajectories, it's actually trajectory distributions, but these kind of linear Gaussian, so linear feedback plus Gaussian noise type controllers, they actually give rise to Gaussian trajectory distributions, which are much more tractable than arbitrary distributions. So what you can do in the stochastic case is you can optimize P of tau, and this is what I talked about on Monday, using a algorithm with fitted local linear models against the surrogate cost, which again is the Lagrangian, and then optimize the theta against a supervised objective by actually running these local controllers on a real system, looking at which states they visit and which actions they take, and using those actions as supervision. And then increment the dual variables. And one of the things that you can do if you apply the algorithm in this way, So here, for this optimization, this is the KL-constrained local models optimized that I described before. If you do it this way, the high-level structure of the algorithm looks something like this. You run your P of tau on the robot, collect your little data set of trajectories. And again, you might use actually multiple trajectories from different initial states or different conditions. Use those trajectories to fit your dynamics. Use those to improve your individual trajectory distributions, just like we discussed on Monday. But then this collection of trajectories is also used as training data to train your neural net with supervised learning. So that's the second step in the algorithm. And the convenient thing is that you can use the same set of trajectories both for fitting your local dynamics and for training the neural net. But there's another kind of neat trick you can do. If you imagine this in a robotics context, it corresponds to running the local model's trajectory optimization. And you can actually visualize that. That's what it looks like. So here, what the robot is doing is it's moving that little wooden block to different locations. And those are the different initial states. So every time you see it moving the block, that's a different trajectory. And it just cycles between them, practicing each of them in turn, collecting data to fit the dynamics. And then once you have that data, you can use it to train a neural net. And the neat thing that you can do is when you train this neural net, you can actually give it a different form of observation as input. So when you're doing the trajectory optimization here with local linear models, you need a state representation that's low dimensional enough that you can fit these linear models with linear regression. When you go and train the neural net, you can give it, for example, raw images as input and just train it with supervised learning on that, and then repeat the process. So if you train the neural net with supervised learning from raw images, then it doesn't actually need to know where the block is for sure. It can just use the image that it's observing to figure out where the block is. So this input remapping trick, which I'll mention also after the break for the other method I'll discuss in this lecture. So the input remapping trick basically means that over here, this constraint, before the constraint was you take the same action in the same state, we can actually change that constraint to say you take the same action in the same state over here. We use an observation over here for the policy. So each state that you saw when you actually ran these things in the real world corresponded to an observation, and the policy gets an observation, but the trajectory optimization gets the state. So at training time, for example, you might have an instrumented environment, maybe you have motion capture, or maybe, as in this case, the robot is actually holding this thing in its hand so it knows where it is. But that information is hidden from the policy. We're just forced to deal with, in this case, the images from the camera. So it gets whatever observations it would actually have at test time. And this is one way that you can actually use this approach to train policies that use high-dimensional raw sensory inputs. I'll show you some videos from an experiment where the policy is actually a convolutional neural network that takes in the image. It processes that image with a few convolutional layers. Then it gets the state of the arm, the right arm here, concatenated to the fully connected layers, and then that outputs the action. So this is kind of like a little robot brain where you can think of these convolutional layers as this little visual processing center, and this is as its motor control center. And this is the paper that does this, and let me show a little video. So this is, oops, start this again. OK. So here it's trying to insert this little red shape into the shape sorting cube using images, and you'll see the pictures that it's seeing later on. Here it's trying to put the coat hanger on the rack, where the rack can be a different distance, so it has to actually look for the rack and figure out where it is. Here it has to put the little claw of the hammer under the nail. And again, the hammer could be, the nail can move around, and the hammer can be held at different angles. And here it has to find the bottle and screw the cap into the bottle. And then we can, let's see if I guess these are all the videos I have. But if you look up the paper, you can see some more illustrations of this thing. OK, so that's guided policy search. Now we're going to take a 3-minute break, and after the break, I'll discuss some other ways that we can train models. We can train policies using imitation. So we'll be back at 11:21. Yes.
Like you said that you have multiple initial states.
Mm-hmm.
So is it like after the end of one trajectory, you kind of like move the arm back to the
Right. Yeah. So for all the things that I showed here, there is basically a hard-coded reset procedure that just says, OK, after you execute one trajectory, reset and move on to the next one. One of the interesting things you can actually do is you could actually imagine learning a reset controller. So you can actually learn controllers for doing the task and a second set of controllers for sort of resetting the environment back to initial states. And then the two controllers are coupled so that one starts in the final state of the other. And that's kind of a fun thing you can do if you have a more complex task.
Like, what is like, because of the first movement, the surroundings were disturbed.
Mm-hmm. Yeah, so this is actually one of the issues if you imagine running real robot experiments with these things, is that you could have like in the process of attempting the task, you might mess things up in such a way that they can't be reset. And that's actually like a pretty substantial practical challenge oftentimes. Yep.
So in the paper on the variational method for constructing trajectory distributions, has there been any like recent work that allows you to optimize like so all these is DDP? Is there any like recent work that uses like other trajectory optimizers to work with like RNNs and stuff?
Right. So the paper that I showed with the virtual characters walking around, that actually didn't use DDP. It used a collocation method. And I'm not sure I understand your question about RNNs.
So the variational trajectory optimization paper, like that one said you couldn't use that it didn't work. It removed it removed like constraints, but like it was still constrained by like not being able to optimize for RNNs.
Right, so the RNN issue, why does that happen? It's sort of the pros and cons of this method. The advantage of this approach is that it decouples all the time steps for the purpose of the policy optimization, right? Because the policy is in the constraints, and if you just separate out all the constraints, they're not actually coupled in time anymore. Which is great because it means you don't have to backprop through time, but it's bad because it means you can't backprop through time, right? So that's where the RNN issue comes in. You can do some fun stuff with RNNs with that method. You can actually add the state of the RNN to the state of the system and actually optimize over the RNN state during the trajectory optimization phase, which is kind of fun because it allows you to train an RNN without backprop through time. But the downside of that is that now it's a lot harder to deal with extremely large RNN states because typically these trajectory optimization algorithms, they're second order, which makes them a lot more stable and efficient. But it also makes them not scale as well with dimensionality because they're inverting these matrices that are n by n, where n is the size of the state. So if the size of your RNN state is like 1,000, then that gets to be really costly. Okay, let's continue. So in the second half of today's lecture, what I'll talk about is another approach that we can use to train policies with imitation learning by kind of stepping back and thinking, well, okay, if we're going to use an imitation learning approach anyway, what if we just look at classic imitation learning approaches? So we said before that if we have this constrained trajectory optimization, it kind of looks a lot like imitation learning because you construct a trajectory, then you imitate that trajectory, and the only difference is that when you construct the trajectory, you have an additional objective term that says, be like the policy. So it's a constrained optimization, but it's also imitation learning. So if it's also imitation learning, why not look at other imitation learning algorithms that we could use and just swap out the human expert in favor of a planning algorithm? So one of the things we can do is we can use Dagger, for instance. And I actually alluded to this before when I talked about this paper from University of Michigan, which used Monte Carlo tree search to figure out how to play Atari games, and then trained a policy to imitate Monte Carlo tree search by using Dagger. We can actually take this idea a little bit further. So there are kind of two problems with Dagger. One problem is this step 3, which is ask a human to label the data, which is a little bit unnatural. So using a computational expert, of course, addresses this because the planning algorithm has no qualms about labeling states that somebody else visited, unlike a human. But there is still another problem with Dagger, which is this step where you actually run the policy. So if you have your, let's say you start the algorithm and you do step 1, you train your policy to mimic some expert. In step 1, the initial policy you get might be actually not so great because you haven't actually addressed the distribution mismatch yet. And then you have to run that policy, collect some data, and then you can address the distribution mismatch. So this step 2, when you actually run the policy, the first time you run it, it might actually be very, very bad. And if you have to run it in the real world, if you're doing model-based RL where you're actually collecting more data and using it to update your dynamics, then this step might result in some disaster. So you can have your car driving over things and things like that. So it would be awfully nice if we could somehow do this step 2, but in a way that's a little bit safer so that we could do this with model-based RL and actually run the policy on real systems without being concerned about them doing some wacky stuff. So one of the things we can do is instead of just running the learned policy over here, we can actually combine model predictive control with Dagger. So if you remember, model predictive control means that you actually replan every time step to choose new actions, which is a bit more robust to model errors. Now the trouble is that Dagger tells us that you really ought to run the policy you're actually learning over here because you want to get data from that policy. So what we can do is we can actually compromise a little bit, and it turns out that we can still get an algorithm with the same kind of convergence guarantees as Dagger. So the way that we're going to compromise is we won't actually run the learned policy, but we'll run a different policy that tries to be similar to the learned policy, kind of similar to how GPS does it. So we'll run some other policy, pi hat, and maybe pi hat is some simple stochastic linear feedback policy that we optimize with LQR, but we'll optimize that simple stochastic policy with an additional term in the objective that says, try to be kind of similar to the learned policy. So what that means is that if the learned policy is telling you, crash into the wall, this thing will say, no, I don't want to crash into the wall because that'll give me a really high cost. So even though I'd like to stay close to the learned policy, I'll say, no, I will not crash into the wall, even if it means violating what the learned policy wants to do, because crashing into the wall incurs a very large cost. But if the learned policy says, drive straight on the road, this guy will say, OK, I agree with you. I can do that. So one way we can illustrate this is if you have this car, the learned policy maybe wants to drive in a particular direction. That's what pi theta wants to do. And then pi hat, it will look at what pi theta wants to do. It'll also look at the long-term cost. And it will choose an action that's close to pi theta, but also achieves good cost, meaning that it doesn't crash into the wall or drive off the cliff. One thing to note about this objective is that over here, we're summing over the cost for all time. But the KL divergence here is only at the current time step. So this is saying minimize cost over all time, but try to match the learned policy right now. When you actually take this action, you might see that now the learned policy wants to do something different, and you might actually replan. So that's why you would use MPC for this. You might replan, change your mind, and then, again, make this compromise between the learned policy and good behavior. And then you keep going. So you replan, which means you're doing model predictive control. And one of the nice things you can do is, just like with GPS that we talked about before, you can use the input substitution trick, which means that your learned policy over here might depend only on some observations, whereas the policy that you're optimizing to actually take actions during training, pi hat, it might depend on the full state. So if you're driving your car, let's say on an instrumented course, you have maybe some, you're learning your policy from images, pi hat depends on the full state, and you're driving your car on some instrumented course, maybe where there's some external observer that gets to measure your full state, but only during training. So that means that pi hat can do smart things. It can avoid getting you into a lot of trouble, whereas pi theta might still be learning from raw images, from sensory signals that are difficult to plan over, but they're the only thing that you'll have available at test time. So this external observer might tell you your state. And the reason that we do this KL divergence over here only at the first time step is that your model is going to predict your future states that you can figure out, but predicting future observations might be extremely difficult. So if your states are, let's say, the position and orientation of your vehicle, where your observations are the images from your camera, it's probably a lot easier to predict your future states than it is to predict your future observations. So it's awfully nice if we can just use the cost here that depends on the state, but only consider the current observation, which we're already seeing. So this is not planning for future observations. It's only planning for future states, and it's using the current observation that you already have access to. And then when you actually take that step, so you know the future x's, you don't know the future o's, and then you actually take the step, and then you observe the second observation. So now you can replan using the second observation that you've just observed in the scale divergence. So one kind of example of how a procedure like this might be used, if you imagine that you need to train, let's say, a little quadrotor to fly around some obstacles, maybe during training, it's learning in an instrumented environment, maybe with motion capture or something like that, so that it gets the ground truth state for replanning, and that replanning procedure is then going to supervise a policy which gets just raw actions, just the observations O. So again, this is the input substitution trick where you get the full state at training time, but maybe not necessarily at test time. And this part over here tells the MPC procedure, stay close to the learned policy so that as the learned policy gets better and better, it will eventually get to on-policy behavior, which means that it's going to address the distribution mismatch problem, and you can actually prove this. And the second term basically says avoid high-cost areas, even if it means that you're going to disagree with the learned policy. So if the learned policy tells you to fly into the wall, it says, no, I'm not going to do that. I'd rather take the hit to distribution mismatch rather than physically take the hit. So this is kind of one way that you can use Dagger for training policies, using optimal control for supervision, and also using the input remapping trick if you want to train it from raw observations. I'll show a little video next. So this is a simulated video, but it's simulating a little quadrotor flying through a dense forest. And here the observations correspond to this fan of laser rangefinders. So they're not quite as high dimensional as images yet, but still a little too high dimensional to plan over. So the planning is being done over the true state during training, and then at test time the policy can just fly using the raw observation. And here it's actually using a little simulated camera. So that's if you want to use Dagger for imitating optimal control, but don't want to run a poorly trained policy in kind of real environments. Okay, and here's a little kind of third-person view. Okay, any questions about this procedure?
When you have that, little trade-off, the tuning parameter, the lambda.
The lambda, yeah.
Does it make sense to sort of change that with time? Like when you start out, stay avoid the high cost region because you think that pi theta is really bad, so
yeah. So the theoretical foundations of this algorithm rest on your ability to enforce the scale divergence actually as a constraint, which means that if you want this to be a constraint, again, use dual gradient descent. What that corresponds to is actually incrementing the lambda based on the amount of constraint violation. Any other questions? Okay. So let's talk a little bit now about the trade-offs between the different methods that we described. So first I'll talk about the specific methods that I discussed in this lecture, and then I'll talk more generally about model-based and model-free reinforcement learning. So in this lecture, I talked about how you can do backpropagation through the full computation graph, but that's not a very good idea because of vanishing and exploding gradients. So one of the ways that you can overcome it is by introducing the policy as a constraint into the trajectory optimization procedure, which makes model-based RL look an awful lot like imitation learning. And there are two methods for this that I described, Dagger and guided policy search. Dagger does not in general require an adaptive expert. So you could use just off-the-shelf Dagger like in the Michigan paper with the Atari and Monte Carlo tree search. So any expert will do as long as states from the learned policy can be labeled. So this can be quite convenient if you have a problem where it's very difficult to do planning and maybe you have some very weird esoteric planning algorithm that you need to use there and can't easily modify its objective to be adaptive to the policy. But Dagger also assumes that it's possible to match the expert's behavior up to a bounded loss. So what that means is that there's an assumption underlying the method that your learner, the learner that's like the p theta, can, given the right data, actually match the expert, which is not always possible, actually. So you can imagine a very trivial example of this. If you're trying to drive that car, but you actually just don't give it the images, you just don't give it any sensory input, well, that problem is actually just impossible to learn. So the best policy pi theta from your policy class might never be able to match the expert, no matter what kind of data it gets. Now that's kind of an extreme case, but you can imagine many realistic partially observed situations where this would be true. So if I'm trying to find the exit from this building, this is an example that I gave in an earlier lecture. If I don't know where the exit is, maybe what I really want to do is I want to exit that door and look around, look left and look right. But if I'm being supervised by a planning algorithm that does know everything about the environment, it'll never illustrate those behaviors to me because it doesn't know about my limitations. So Dagger assumes that this kind of discrepancy does not exist, meaning that if you get data from the right distribution, you should be able to match it up to a small bounded loss. So it's not always possible in partially observed domains. Guided policy search adapts the expert behavior, which means that it doesn't require the bounded loss on the initial expert because it has that constraint that goes both ways. But of course, the trade-off here is that it requires you to be able to go in and modify your trajectory optimization algorithm to incorporate that additional policy loss. OK, so those are the methods that I described in today's lecture. Now, why might we want to use approaches like this? Why might we want to imitate optimal control? Well, for model-based RL methods, these are relatively stable and easy to use. One of the things to consider is that we do have very good supervised learning algorithms that tend to work pretty well. They tend to be a little easier to use than a lot of alternatives. And optimal control generally works fairly well. It's a fairly well understood class of methods. So the combination of the two often works very well. You can use the input remapping trick. So if you need to do your optimal control over low-dimensional states, you can still incorporate high-dimensional observations into the policy. And this kind of stuff can overcome the optimization challenges of backpropagating to the policy directly. So in general, model-based RL algorithms tend to be more sample efficient and for that reason a little bit more viable for real physical systems, but typically at the cost of introducing additional assumptions. So here's a summary of the model-based RL methods that I covered. We talked about on Monday about methods that learn the model and then plan, basically without having a policy at all. So these methods iteratively collect more data and use it to overcome the distribution mismatch. So that's often a very good idea. You can also replan every time step with an MPC type approach to mitigate model errors. And this is actually the version that you'll be implementing for homework 2. You'll have an algorithm that collects more data to overcome mismatch and replans every time step. But you can also have model-based RL algorithms that learn the policy, backpropagating into the policy as an example. That's what actually the Pilko algorithm that I talked about on Monday does. Simple, but potentially a little bit unstable. You can imitate optimal control in a constraint optimization framework with GPS, or you can do it in other imitation learning frameworks like Dagger. There's actually other choices for using model-based RL to learn policies. So one example that's not covered on this slide is something called the DINA algorithm. And the idea there is you might say, well, I actually really like model-free reinforcement learning. Like I'm pretty good at writing model-free reinforcement learning algorithms. So can I just do model-free reinforcement learning, but use a learned model? So what DINA actually does is it says, let's train a model, but then let's use that model essentially as a simulator. So let's train some kind of function approximator like a neural net as a model, and then generate synthetic experience from it and give it to a model-free reinforcement learner. And that can actually be like a fairly simple way to get some kind of model-based RL method to work if you already have a model-free RL method and you're just not happy with the sample complexity. So that's another alternative that I didn't cover in this lecture. What are some of the limitations of model-based RL? Well, you need some kind of model, which is sometimes straightforward and sometimes actually extremely difficult. So there are a lot of situations where you might have extremely complex dynamics that govern the environment, but a relatively simple policy. And in those cases, it might actually be easier to learn the policy directly. The model might not always be available. You might need to learn it, and sometimes it's actually harder to learn than the policy. Learning the model takes time and it takes data. So oftentimes, actually, computationally model-based RL algorithms are quite a bit more expensive than model-free algorithms. They're typically more efficient in terms of the number of samples that you need, but again, it depends on whether it's much easier to learn the model or much easier to learn the policy. So sometimes very expressive model classes, like neural nets, are not actually all that fast, depending on the specifics of your problem. And sometimes fast model classes, like linear models, are not expressive enough to model the dynamics of your very complicated system. Typically, model-based RL methods introduce some additional assumptions that are often not present in model-free methods. So if you're using, for example, local linear models, the additional assumption you're introducing is you're saying, well, I believe that my system is continuous and that it can be at least approximately linearized, which is true for some physical systems, but obviously not true for like discrete systems like Atari games. Oftentimes, model-based RL methods assume some ability to reset your system, especially if you're using local models, which means that you can try multiple times from the same place. Some model-free methods assume that also, but oftentimes they can work fairly well in an online setting. And then some model classes, like the GP models used in Pilco, assume that your system is actually fairly smooth. So not just continuous, but actually smooth, and doesn't have kind of non-differentiable events like contact dynamics that you get in locomotion. And then a bunch of other assumptions that depend on the particular method being used, the particular problem setting that you're solving, and so on. So in general, it takes a bit more work to get model-based RL methods up and running for a new problem because of the additional assumptions they might introduce. So, one example of a, some system with a very simple behavior, if you're trying to hold the cup, you just grip the cup as hard as you can, but the underlying physics might be fiendishly complex. Now, one of the things I wanted to do in the remaining time for today's lecture is go over also some trade-offs, not just between different model-based methods, but also between different model-based and model-free algorithms, because at this point, we've actually introduced all of the major categories of model-free methods, and we've covered model-based RL. So from here on out, starting next Monday, we'll have more advanced lectures about sort of researchy topics. So now that we've got all the basics in place, seems like a good time to summarize some of the relative trade-offs to maybe give you a little bit of an idea if you're trying to tackle a new problem with reinforcement learning, what are some of the considerations that might matter. So one consideration that often matters with reinforcement learning algorithms is sample efficiency. So if you want to use reinforcement learning to solve a problem, if you're actually collecting experience, either in an expensive simulator where simulation is non-trivial in cost, or even on real physical systems, or real virtual systems where collecting experience does have a pretty substantial overhead, a question you might ask is, well, how sample efficient is the algorithm that I'm using? And we can look at sample efficiency of different algorithms. It's a little difficult to compare all of them directly to each other because not everybody does comparisons on the same benchmarks. But sort of back of the envelope calculation, we can do it like this. Typically, the most expensive in terms of sample complexity algorithms are gradient-free methods. So we didn't cover these in the model-free section, but these are methods like natural evolutionary strategies, CMAES, and so on, methods that don't actually compute gradients through the neural network, but rely on stochastic optimization procedures. A bit more efficient, but still relatively expensive, are fully online methods like A3C, so actor-critic methods that use an online learning procedure, don't keep a replay buffer of off-policy data, and rely on basically massive parallelization to keep multiple batches. A little bit more efficient than that are policy gradient methods that use sort of batch mode optimization rather than online optimization. So these are still on policy, but now they're batch mode, and they tend to be a little bit more efficient. A little bit more efficient than that are methods that actually are off policy that use a replay buffer. And this is where you get a lot of the value function-based methods that I covered, things like Q-learning, DDPG, and so on. Model-based RL methods are typically more efficient than that. And then shallow model-based RL methods, meaning model-based RL methods that don't use neural nets, are even more efficient than that. But once you start going down here, now you're also introducing some additional assumptions, and they start getting pretty restrictive once you get down to the bottom here. And each of these sort of rungs in the ladder actually has a sample complexity difference of about 1 order of magnitude. So this is an example of a paper that uses stochastic search, evolutionary strategies, and their reported results on standard benchmark problems are about 10x more samples than fully online methods like A3C. So for most of these comparisons, what I'm going to use is this simulated cheetah task, which some of you might have tried on homework 1. Now, there's an important caveat here, which is that the cheetah task has sort of evolved through time and space, so it's not always the same exact cheetah task. So these are not exact comparisons, but they're like rough order of magnitude comparisons in terms of sample efficiency. So what the evolutionary strategies paper reports for cheetah, about the equivalent of 15 days of real time. So if the cheetah was actually running around, it would be running for half a month. For the fully online A3C style methods, oh, sorry, this is 15 days of real time. This is for A3C. So for this one, it's about 10x that. So it would be running around for half a year, half a month for A3C. Of course, when the algorithm actually runs, it doesn't take 15 days because the simulator is much faster than real time. But if it was an actual cheetah, 15 days. If you look at the kind of state-of-the-art result for a policy gradient style method. This is something called trust region policy optimization. There, the reported sample complexity for cheetah is 1.5 days, so about a 10x improvement. If you look at a good implementation, in this case of DDPG, for solving the cheetah, it's about the equivalent of 3 hours of real time if the cheetah was actually running around in real time. So that's about a 10x improvement. And in fact, there's some experiments, I think I showed this in the value functions lecture, some experiments on real robots with NAF, which is also a Q-learning style algorithm, also shows training times of about, in this case, 2.5 hours. So probably fairly reasonable to conclude that for this style of task, on the order of a few hours is about what we should expect. So again, it's about a 10x improvement. I should say that by the time we get over here, now we're actually starting to get into the regime where computation time, even when you're running things in real time, the computation time actually sometimes matters more than data collection time. So right around the 3-hour mark is probably about where the time it takes for you to train your neural net starts to even out with the time it takes for you to collect your data, even if you're collecting your data in real time. Up here, if you were collecting data in real time, you're entirely bounded by data collection. As you move further down, now you're going to be basically completely constrained by computation time. So if you go to like model-based RL methods, this is a comparison on a slightly different task now because there isn't a cheetah comparison here. But again, it's about a 10x gap. This is on a reaching task against, this is a 10x gap against DDPG. So again, about 10x. So here we're talking about tens of minutes of training time. And if you look at shallow RL methods, now here the trouble is that the tasks are completely different. But for shallow RL methods, it's not unusual for them to report training times of a minute or less on relatively simple benchmark problems. So probably reasonable to surmise there's about a 10x jump there as well. So this hopefully gives you some very high-level, back-of-the-envelope calculation about what to expect from sample complexity of different methods. And it's probably fairly reasonable to say that the cutoff between what's feasible to run in real time and what's not lies somewhere around here. So if you go down to this area, this is reasonable in the order of a few hours. If you go up here, this is starting to get pretty tough. This is where you pretty much want to have a simulator available. So going off of, oh, and by the way, one thing I should say here is, well, OK, if you just look at this picture, one might wonder, well, why the hell would you want to do the stuff that's up there? And part of the reason that you might want to do the stuff that's up there is that if you, instead of looking at sample complexity, if you instead look at wall clock time in a situation where you have a trivially cheap simulator, so if you have a very fast simulator for your system, the picture for wall clock time is actually upside down. So if you have very good parallelism, if you have access to many machines, then in terms of wall clock time, this thing actually tends to be the fastest, and it actually goes backwards. So if simulation is cheap, the pecking order is flipped, but if simulation or real-world experience is expensive, and you just care about sample efficiency, then this is the order that you're looking at. So one of the things we can do going off of that is we can create a very rough sort of flow chart to try to understand what kind of algorithms should we use depending on the properties of our problem. And please take this with a grain of salt because, of course, every problem and every algorithm is a little different in certain ways. But if you just want sort of a very quick kind of rule of thumb, you can say, which RL algorithm should I use? Probably the first question you should ask is, are you learning in a simulator? And if you are learning in a simulator, the next question to ask is simulation cost negligible compared to training cost? So basically, are you in a regime where running backward passes through your network is actually more expensive than taking steps in your simulator? And if you are, and if that is the case, meaning simulation is trivially cheap, then this is where the algorithms that are sort of at the top of that heap on the last slide are preferred. Things like policy gradient, fully online methods like A3C, and so on. This is where you might want to use those methods because they'll be likely faster in terms of wall clock time, and also in the case of policy gradient algorithms, probably actually substantially easier to tune and set up in terms of their hyperparameter sensitivity. So if you're running in a simulator and your simulator is cheap, this is probably a good place to start. If you're running in a simulator, but your simulator is not cheap, then, so this is an example of TRPO, learning to walk in a simulator. If it's not cheap, then you might want to look at value-based methods, things like Q-learning, DDPG, NAF, double Q-learning, etc. Things where you need a substantial amount of experience, but you can still do off-policy learning using a replay buffer to improve your efficiency. That said, if you're learning in a simulator, Another question that you might want to ask is, if you already have a simulator, you can probably actually compute gradients through your simulator. Even if you can't compute them analytically, you can probably compute them numerically using finite differences. So it's also worthwhile to ask, especially if you have a continuous problem, if you can simulate experience through your simulator, do you actually need model-free RL? So are you better off, for example, doing something like Monte Carlo tree search, or if you have a continuous problem, maybe doing something like the tree structure optimization method in this work? The answer, by the way, is not always yes. So there are cases where model-free RL methods like policy gradients might actually do better than the analytic planners, but it's something that's worth considering. Now, if you're not learning in a simulator, then the important question to ask is sort of how patient are you? And how patient are you is also very closely related to, can you collect data autonomously? So is the way that you're doing things not in a simulator involving manual labor? Like, is somebody physically present there overseeing an experiment, or is there if you're doing some industrial tasks, do you need somebody there ready to stop the algorithm if something goes wrong? So that's the question to ask there. So if you are impatient, then perhaps you might prefer a model-based RL algorithm, and you might prefer to do the extra work to actually set up that model-based RL algorithm, make sure the problem meets its assumptions, choose the model class, and so on. And if you're a little bit more, so this is the model-based RL examples that I showed. And if you're a little more patient, if you think you can wait, maybe try to go for the efficient model-free methods. And this is the result for the real world with the value function methods. OK, so this is, as I said, take this with a grain of salt. Obviously, every problem is a little different, but hopefully this can at least give you some initial ideas, some initial rule of thumb to get started in choosing the right RL algorithm for the job. Does anybody have any questions about this? OK. Well, so starting next week, we'll have more advanced lectures. Actually, on Monday, we'll have a guest lecture from Chelsea Finn on advanced model-based methods, and then we'll continue from there. So see you all next week.